All right, let's look at some problems that'll help us review for our second test over chapters 2 and 3. So one of the problems we had was a polynomial function like this that is all factored out, where we have all the factors so that we can find the zeros and everything else. Now, if you look at this, the degree is just the total number of factors. So I have 2 here, 1 here, and 3 here. So 2 plus 1 plus 3 is simply 6. Now, I also know when I'm trying to figure out kind of what this graph looks like so I can talk about its end behavior. So if I look at this graph, the number in front is a negative leading coefficient. So if you recall, we said odd degrees were kind of S-curve, snaky shapes, and even graphs were going to be more parabola-like. Well, since this is degree 6, it's going to be even, but the negative, remember, is going to make it flip upside down. So it's going to look something like this. A parabola is upside down. If you graph this in the calculator, you would see it looks like this. So in this case, as x goes off to infinity, f of x is going to negative infinity. And that's also true as it goes off to negative infinity. You can see as this goes to negative infinity, it's also going down. So we'll say f of x goes to negative infinity. Now, one of the other things we tried to do is we tried to find the zeros, the multiplicities of this, and tried to sketch the graph of it. So if you look at this, it says find the zeros of this function and determine the multiplicity. And then we could also talk about whether it touches or crosses. So let's talk about each zero, its multiplicity, and let's talk about whether it touches or crosses the x-axis. So each one of these factors is going to produce a zero because it's already in factored form. So this first factor, x plus 2, will give us negative 2. And its multiplicity is 2 because its exponent is 2. And remember, if it is even, then it is going to touch the x-axis. Similarly, down here, we know it's 4. And the multiplicity is just 1 because there's no power on that factor. So this is going to cross. And finally, we have negative 5, which is the last factor, multiplicity of 3, which is going to cross as well. Remember, even multiplicities will touch and bounce off. Odds will cross through. So this one just says sketch a graph of f of x and label the x-intercept. The only other thing we could find is the y-intercept, but if you find the y-intercept, remember y-intercept is when you plug in 0. It's going to be just huge in this case. It's negative 3 times 2 squared times negative 4 times 5 to the third power. Now the big thing I can tell you this, you can multiply this out, it's fine, but it's a big positive number, right? Which is going to kind of make sense with our graph shape up here. So if I'm going to sketch this, and I wish I wouldn't have labeled the axes with numbers, but it's okay. So we're going to have an intercept at 2, an intercept at 4, and an intercept at negative 5. I know it's going to start going down, going from the bottom, going up, pardon me. At negative 5, it crosses. It's got to turn around somewhere. It's got to go to negative 2 where it touches. It's going to bounce up. Now it's going to go way up to this y-intercept, way off the graph. And then it's going to come back down, and it has to cross at 4. So you can see this does look like that parabolic shape. As you're going off to infinity, it's going down. As you go off to negative infinity, it's going down. But we just tried to sketch these graphs based on the intercepts we know. All right, the second problem says if you have a degree 3 polynomial p with real coefficients, which has 0 of 3 and 1 plus I in factored form. Now, of course, since it's degree 3, we should have 3 zeros. Now, in this case, we know one of them is 3 and one of them is 1 plus I. So we have to determine what that third zero is. Well, if you recall, we said that if you have a root or a zero that has an I in it, a complex root, we know they have to come in pairs. So if 1 plus I is a root, then 1 minus I would be a root as well. So these are our 3 zeros, and we simply want to write this in factored form. So we can say P of x, remember we just take x minus the root. So it's x minus 3, x minus 1 minus I, just taking the opposite of both of those, and then x minus 1 plus I. Now, if you wanted to get this in standard form, you would have to FOIL this all out, multiply all the binomials and trinomials together, and you could get that, but in this case, we're just looking for factored form, so this is fine. I don't really know anything about the a value. We could put a number out here. If it's negative, it flips it over, but we don't really know any information about that, so we will just keep it in the simplest one we know, which is this one. All right, the other kind of big problem we did in Chapter 2 was finding zeros of polynomial functions when they're not in factored form. The first problem was really nice. They were all factored, so I could find out what the zeros are pretty easily. But this one is not. This one is in some kind of other form that I have to try to find the zeros. Now, I do know there are 3 of them. There are 3 zeros because the degree is 3. And the fundamental theorem of algebra says that we're going to have that many zeros. They could be imaginary, they could be real, who knows, but those are the ones they have. So first thing we'll do is we'll look for possible rational zeros. We'll start looking for rational numbers. Rational numbers, things that can be written as a fraction. And those are in the form P over Q, where P is factors of the last number and Q is factors of the leading coefficient, which is nice because Q is just 1. So the leading coefficient is just 1. And then I can just list factors of 12. 1 and 12, 2 and 6, 3 and 4. So my total rational zero list, if I divide them all by 1, is just this list. So I went ahead and I graphed this in Desmos to kind of see what it looks like. So I'll just kind of sketch what I see here. It looks something like this, goes up, down, then almost immediately up. Now, this one is reading as 3, 0, which is definitely good. So 3 is going to be one of my zeros. The one over on the left is reading as negative 1.236, comma 0. So that is a 0, but it's not the right one. It's in the irrational decimal form, so we can't use that. So we'll have to figure out what that one is exactly. And this one is similarly saying 3.2360, which we can't use either, so we'll have to figure out those another way. But we can find those knowing this 3 is a 0 because we can divide out. So if we recall, once you have one of the zeros, you can divide out 1, negative 5, 2, and 12. So what we'll do is we'll do our synthetic division. 1, 3, negative 2, negative 6, negative 4, negative 12, 0, which is good because you want a remainder of 0. So this is going to leave us with x squared minus 2x minus 4 because that's 1 degree less than what we started with. We had a degree 3, we divided it out once, we get a degree 2. We'll set this equal to 0, and we will solve this using quadratic formula. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. And so we'll just plug in and solve. So we get 2 plus or minus the square root of b squared, so that's negative 2 squared, minus 4 times a times c all over 2a. So if I figure out what that discriminant is, that's 2, that's going to be 4 plus 16, which is root 20 over 2. I can simplify root 20 to 2 root 5 over 2. And that's simply because, remember, root 20 is root 4 and root 5, which is 2 root 5. And then now all these numbers are 2, so I can divide them all by 2. So 1 plus or minus 1 root 5. So in this case, our other 2 zeros were not imaginary, they were irrational. Those weird decimals we saw on Desmos are simply 1 plus square root of 5 and 1 minus square root of 5. So those are my 3 zeros. So this is obviously a big part of what we did in the last chapter. Finding possible zeros, dividing it out, getting to a quadratic we could solve. Now sometimes you didn't have to do quadratic. If the x was missing, we didn't get that lucky in this case. So now if I want to write this as linear factors, I just do x minus the 0, so x minus 3, x minus 1 minus root 5, x minus 1 plus root 5. So this is the factored form of my initial polynomial. But it's definitely a process you have to go through to solve these kind of problems, getting them from the standard form to the factored form, unlike the first problem that we had on the first page where it was already factored. All right, question 5 is about a rational function that we see here. So this is when we have a numerator and denominator, and we're trying to find all the parts of it. So first thing we're going to do is obviously factor. So if I look at this, I can see that first I look for a common factor, which the top has a 4. So I'll go ahead and factor that out initially. The bottom does not have a common factor. It will factor, but it doesn't have a common factor. And then if I look at this now, I'm going to look at the top, which is difference of two squares. It's x squared minus 1, both perfect squares. So that'll factor as x minus 1, x plus 1, over. And then if I factor the denominator, two things that multiply to negative 9, add to negative 8, are minus 9 and plus 1. So this is my factorization. Now before I obviously start canceling, which we can see something cancels, I'm going to make sure I do my domain, which is going to be, I'm going to exclude the numbers 9 and negative 1, because those are what make the bottom 0. Those are what's going to create my undefined values. So my domain is negative infinity to negative 1, negative 1 to 9, and 9 to infinity. This is the same thing as all reals except for negative 1 and 9, because putting the parenthesis on both sides of those numbers is what is going to give you that. So now I'm going to go ahead and cross out the x minus 1. I know that's going to give me a hole at that location, so I know I'm going to have a hole at negative 1 comma something. But the good news is now that I cancel it out, I'll have everything I do is going to be based on this lowest terms. This is my lowest terms function now, which is 4 times x minus 1, or if I wanted to distribute that 4, I could use that too. So both of these are fine to use depending on what I want to use. So I'm going to go ahead and finish up the whole initially. So I know the x is negative 1. To find the y, I'm just going to go ahead and plug that into the lowest terms. So I'm plugging it into this version of lowest terms. You don't have to. You can do it in the other one. So I'm just going to plug it into that version of the lowest terms. So that's negative 4 minus 4, which is negative 8. That's negative 1 minus 9, which is negative 10. That's 8/10 or 4/5 if I reduce it. So my whole is at negative 1 and 4/5. So I'm going to go ahead and come down here. I'm going to look at negative 1 4/5, which is about 0.8. Kind of hard. I'll zoom in here. Negative 1 and 0.8, so there is my hole right there. So now I have 1 point on my graph. Now as far as some of the other things, intercepts, so let's start with x-intercept. X-intercept is what makes the top 0 when in lowest terms. So if I look at my lowest terms over here, my top here, I have 4 times what minus 1 is 0. Well, I can kind of ignore the 4 because 4 is just a number. It's never 0. What number minus 1 is 0? It would be 1. So I have an x-intercept at 1, 0. Okay? So I can put that on my graph down here. That's pretty easy to see. That's going to be there. Now as far as y-intercept, remember, we are going to put 0 in for x. X-intercept is the top equals 0. Y-intercept, we have to plug 0 in. It's going to be 0 comma something. I would probably plug it into the lowest terms, 4 times 0 minus 4, 0 minus 9. So that's just negative 4 over negative 9, which is just positive 4/9. Now 4/9 is 0.4444444, which is kind of what the Desmos would tell us probably. So I'm going to say that's somewhere right about there. So I've got 2 points and I've got a hole for my graph. So now I got to find vertical or horizontal or slant or oblique asymptotes. Now vertical asymptote, remember the vertical asymptote is what makes the bottom 0 when in lowest terms. So that's going to be x minus 9. So what number minus 9 is 0? Well, it's 9. So x equals 9 is my vertical asymptote. So if I start to sketch my vertical asymptote at 9, it would look something like this. So almost off the graph. Now horizontal or slant is based on the degree. So if I look at the degree I have here, so my degree of this guy is 1 and this is 1. When the degrees are the same, remember we divide the leading coefficients. So it will have a horizontal asymptote, and it's at y equals 4 divided by 1 because those are the leading terms. Make sure on your test when you write asymptotes, you're writing them as x equal or y equal. That is very important. So at 4, this is going to have an asymptote that looks like this. Okay? So I've got my x-intercept, my y-intercept, my hole, my vertical asymptote, my horizontal asymptote, all based on my equation. And obviously you can use the graphing calculator to kind of fill in what this looks like, but just based on what I know, I'm going to guess it's going to go through those points, so skips the hole. That's pretty terrible. Let me start this again. Maybe I'll start down here. It might be a little easier. Going to go something like this. Get real close to that hole and touch. Kind of keep going like that. Something like that. And then it'll do a similar thing up here where it would kind of go like this, obviously off this graph. But it would not be down here because then it would have more x-intercepts, which you know it doesn't have. So it's going to look something like this. The key thing is you just want to make sure that you have your hole labeled, your intercepts labeled, your asymptotes labeled. Beyond that, just sketch it as best you can. So that is a complete problem for that rational function. Last type of problem I want to look at is our inequalities we did. So we have a polynomial and a rational inequality here. So the idea here is when we're going to set up our sign chart. So I'm going to look at what the zeros are for this polynomial equation. So I have each parenthesis is going to give me a 0. So -2, 2, and 4. And then I'm going to set that up on my number line. So I'm going to draw my number line, put those numbers on there, -2, 2, and 4. That will break us into 4 regions, A, B, C, and D. So the goal is to pick a number in each region and see if it's negative or positive. So I'll pick -10, that's less than -2. A number between -2 and 2 is 0. A number between 2 and 4 is 3, and then we'll go with 10 as a number bigger than 4. So for region A, I'm going to go ahead and plug in -10. So I'll get -10 plus 2 to the third times -10 minus 2 to the second times -10 minus 4. Now, I don't really care if this is negative or positive, or with the numbers, I just care if it's negative or positive. So if I simplify this, I know this is -8 to the third power, which is going to be negative because it's 3 negatives. I have -12 squared. Well, anything squared is positive, and then -10 is going to be -14, which is negative. Now, you are certainly welcome to just type this in your calculator and figure if it's negative or positive, but this is going to give me a negative number of some sort, right? And in this problem, since we're looking for things that are less than or equal to 0, and I got negative in region A, I would want to include region A in my solution set. And then I'll do the same for B, C, and D. So I'll do B. B is 0. 0 plus 2 cubed. 0 minus 2 squared. 0 minus 4. So this is going to give me 2 to the third power, which is positive. This is going to give me negative 2 to the second power, which is positive. And then 0 minus 4 is negative 4, which is negative, so this is negative. Now, of course, if you didn't notice, I did make an error that I just saw. So let's go ahead and go back and fix that. So region A is not good because if I have 2 negatives and a positive, this is actually positive, right? Which I don't want positives, I want negatives. So that is my mistake. So we do not want region A, we want region B because it is negative. So my mistake. So C, let's look at C. We'll plug in 3. 3 plus 2 cubed, 3 minus 2 squared, and 3 minus 4. Well, that's 5 to the third, which is positive. That is 1 squared, which is positive. And 3 minus 4 is negative. So 2 positives and a negative is a negative, right? And I don't want negatives, I only want positives. So it usually does alternate plus, minus, but it doesn't have to. In this case, it actually doesn't. And then region D, I'm going to plug in 10. 10 plus 2 cubed, 10 minus 2 squared, 10 minus 4. These are all positive. It's 12 cubed, which is positive. It's 8 squared, which is positive. It's 6, which is positive. So I get a positive, right? So I do want, I want negatives again. So I want region C. I do want negatives. I don't want positives. I'm just messing this one all up. So I want region B and region C. Okay? So region B and C are from, so you can write it a couple ways. It's region B is from negative 2 to 2, and then region C is from 2 to 4. Although, because these are all bracketed because it's included and there's no real gaps, you could just write this as negative 2 to 4 because you're including the one that breaks them apart. But either way would be fine. Obviously, just make sure you plug in, see if it's negative or positive, and that's all there is to it. All right, let's look at this last one, which is a rational inequality. So this one we got to figure out what makes the top and bottom 0, which obviously we can't because it's not factored. So what I would do is I would factor, so the top I could take an x out, and so I get x 2 minus x. And on the bottom I'll get x plus 5, x minus 1. Two numbers that multiply to negative 5 add to 4, and then just the GCF on top. Still less than 0. So now if I want my zeros, that's what makes the top 0, which would be 0 because of this factor, and then just 2 because of 2 minus some number being 0 is 2. I also have some excluded values, which are going to be what makes the bottom 0, and that's going to be negative 5 and 1. So we got quite a few values here to put on our number line. Smallest one being negative 5. And then 0, and then 1, and then 2. So in this case, we have A, B, C, D, and E. So we have 5 regions. So we'll pick a number in each region. So a number smaller than negative 5, let's go negative 10. A number between 0 and negative 5, let's go negative 3. Now these get trickier. Between 0 and 1, we might have to use like 1/2. And then between 1 and 2, maybe 1.5, and then some number bigger than 2, which is 10. So the fractions might be a problem, but again, we only care if it's negative or positive. We actually don't care about the value, so that'll make it a little easier. So we have A, which I'll plug in negative 10, so it's negative 10 times 2 minus negative 10 over negative 10 plus 5. Times negative 10 minus 1. So that's a negative times a positive, because 2 minus negative 10 is positive 12. And then on the bottom, we'll get negative 10 plus 5, which is negative. Negative 10 minus 1 is negative 11. So we have three negatives, two negatives on the top, two on bottom. This is a negative divided by a positive, which is a negative. Now in this problem, we're trying to figure out when it's less than 0. So we do want negatives, so we'll take region A. So now we'll go to region B and do the same thing. We're going to plug in negative 3. So negative 3 times 2 minus negative 3 over negative 3 plus 5 over negative 3 minus 1. So that's a negative, a positive, because it's 2 minus negative 3, a positive on bottom, and then a negative on bottom. So we get a negative on top, a negative on bottom, which two negatives divided is a positive. We want negatives, so we do not want region B. So we'll just keep doing the same process. We'll go to region C, which is half, which is going to be kind of bizarre. So it's 1/2 there. Then we're going to go with 2 minus 1/2. Those are both positive. And then on the bottom, we have half plus 5. I don't know what that is, but I know it's positive. And then half minus 1 is negative. So that's a positive over a negative, which is a negative. That's what we want, so we want region C. Region D, we're plugging in 1.5, so 1.5, 2 minus 1.5, 1.5 plus 5, and 1.5 minus 1. Everything is positive here, so this is, of course, positive. And we don't want the positives. Now let's do region E over here. E, we're plugging in 10. So we have 10, because it's just x, 2 minus 10, which is going to be negative. And then we have 10 plus 5, and then 10 minus 1. So this is a positive, a negative, a positive, a positive. So it's a negative over a positive, which is a negative, which I want. So we have three regions in our answer. Now the nice thing is there's no equals to, so it's all going to be parenthesis. So negative infinity to negative 5, union 0 to 1, union 2 to infinity. Now, if you did have the equal to, remember, you could put a bracket on any 0, just never put one on an excluded value. So, check this out. If you have questions, bring them to class. We can talk about them in preparation for our second test. Minus 4